Okay, I'm going to introduce you here to Blast, kind of work through a very simple problem with it. And what we're going to do is first go to Google, and I'm going to search for NCBI and Blast in. All right, so we can go to Blast, which stands for Basic Local Alignment Search Tool, but we're specifically looking for Blast in, which is Blast based on nucleotides. There are other types of blast, which I will talk about, but here we're just going to stick with the basic nucleotide blast, meaning DNA and RNA. So we go here, and here is what Blast looks like. Essentially, this is a Google search engine for sequences, or it is a search engine. So you search just like you would for Google on Google, and you can type in the sequence, whatever you want if you want to do it the slow way, or cut and paste into this box. But there is another way, which we're going to use, which is we're going to choose a file. So I'm going to click Choose File here, and then I can go find something, and I'm going to choose this one. Now this one is something I already know something about. This file is a large nucleotide sequence, about 8,000 bases long, and it includes 2 genes. I know one of those genes is GPX1, and it's in humans. So this is a large sequence that is about 8,000 base pair. And the first gene in there is something called RHOA. And then there's a little gap between them, of course. We need all those regulatory sequences, some separation between the 2 genes. And then there's a second gene, which is GPX1. And this is how it works in humans. And so you can ignore all of these things for now. We'll go back and look at all of the things you choose here. You scroll down, and just for a regular search, you would just hit Blast, and you'd hit it here. Now, it would probably take you a minute, maybe a minute and a half for a large sequence like this to be run on Blast. So I've already got the results, but all I did here was I found the file, hit Blast, and what you come up with is this as a result. So this is your resulting page. And you normally would, like I said, would have to wait maybe a minute and a half to get a result. But when you get it, these are your results. And what you can do, you scroll down here. I'll explain the top part in a second, but you scroll down, and of course the number 1 hit is Homo sapiens glutathione peroxidase 1 reference gene on chromosome 3. This is actually what I downloaded. That file is this sequence here. And of course, it's 100% identity. That means base per base, every base is the same. And its e-value is 0. That's the best you can do. For an e-value, you want as small a number as possible. Query cover means the entire thing, essentially both of these. In other words, one's kind of comparing the sequence and how much of the sequence you put in is covered by the sequence in the database, and then the other one is the opposite. They're kind of looking at it. So they might not be the same size. These are, of course, identical. They're the same thing. And you would get like 100% on one, and maybe if it's half the size of the thing you're searching for, this might be 50%. So just keep an eye on these. These don't matter as much. The e-value is the thing we normally go by, and the smaller the better, and you're not getting any smaller than 0. Total score, I usually don't go by total score, max score. Most people go by e-value, and for nucleotides, RNA or DNA, you want it to be at least 10 to the negative 5th or smaller. So right now 0 is as small as you can get, because, well, we're actually getting the exact file that I downloaded. So that's the first one. Now all of these, if you'll notice, this is another piece on chromosome 3, essentially the same. Here we get, this is the first gene on there, RHOA. And then we get GPX. Now you'll notice that it's these numbers are a little different, because now we're comparing it. The result was a smaller piece than the one we put in, so it found a small piece of the of the file I put in that's identical to something. So we get smaller numbers here. Again, we expect this. 99, we'll get 100% variant here on mRNA. Of course, that's smaller. So here it's only 16% of the whole file. So we drop down. Now we look at it, and we get down here. You can still see it's 0, so we're getting identical things. So these are all human, but no, wait a second. The first thing we get that's not human is gorilla. All right, gorilla was the first organism, and you'll notice that it's also 0. In other words, the E value, it's essentially identical. It hasn't changed, I guess, at all. Has it not changed at all? Let's go back up here. Percent identity, query cover, yeah. So the gorilla version is closer than the, let's see, there's a pan troglodytes. That is a chimp, and it doesn't look like it's changed. If it's changed any, it's only a few bases. And let's see, we'll scroll down, and then we get, I don't know, that's some type of monkey here. These are monkeys. Yeah, so pan troglodytes, this is bonobos, very similar to chimps. Yeah, so you get the idea that this gene, it finds the things that are closest to it, and you either find the gene itself, one of the genes or the others, and you find it in very highly related species. Here's one. It's GPP binding. No, that's RHOA. All right, so it's still the same. But I just wanted to show you. Here's the pseudogene. That's a gene. It's a copy that no longer works. And I thought I saw the pseudogene for GPX1 up here too, somewhere in here. No, maybe not. But so that's very similar. But notice you're seeing the variants. These are the variants of RHOA or a variant of GPX, but you're not seeing GPX2 or 3 or 4 or 5. All right, here's a pseudogene for Rho. But you don't see the GPX1s too. That means they diverged quite a while back before even we diverged from apes. That's what we were here, because we see the apes are similar to us for GPX1. That means we actually gained these GPX genes at a point in time before we diverged from apes. So the GPX1 is more closely related to the GPX1 in gorillas or chimps than it is to GPX2, 3, 4, 5, 6, 7, 8. In other words, they are further distant in sequence than the GPX1 in another organism. So GPX1 in humans and apes is pretty close, but GPX closer, much closer actually, than GPX1 is to GPX2. This indicates that these genes separated and were duplicated at some point way back in history, back when we were not human yet, before, who knows how far back. But they still can be, because there are structural reasons, chemical structural reasons that lead to the function of it. They still have to maintain some similarities to between them so that they function correctly. There are some things that are required for you to be a GPX gene, period. All right, just wanted to show you this. This is what you can do with Blast. There are actually different things. If you want to, if you go here and want to see, let's just start with something that's a little different. I'll just start here. No reason I'm picking this one, but I'm going to click here so we can see. Here are the two sequences aligned. So you can see that, you know, okay, here's a one change right here. There aren't many. Here's a change. This would be a deletion. Or it could be an insertion on the other side. It's either an insertion here or a deletion here. It depends on the perspective. Same here. You get a few changes. But generally, it's the same across two species from, this is some type of monkey. Pongo abeli. It's an ape. I'm not sure. Maybe it's an orangutan or something. But there we go. That's where you can see it. Now let me go back. There we go. Okay. Oh, too far. All right. Now you can also go over here and get the actual sequence itself if you want the new sequence. This is the comparison between the two. If you want the new sequence that it is related to, you can go here and you can get the FASTA file or the GenBank file for that piece. A little slow here. We're waiting for it. I'll go back. The whole system was down on Thursday, so it is a little finicky sometimes. Here we go. GenBank file. If you want the FASTA, you come up here to send to file and choose FASTA, and then you can create file, and it will download it for you. So that's how you would get the FASTA file for this sequence that compared well with our original sequence that had 2 genes. You can also click here for FASTA if you want to see the FASTA. You don't just want to download it, but you can get the FASTA that way, like this. All right, now let's go back. Oh, come on. No, it's not going to let me. Okay, I want here. All right, so the other thing we can do is we can go up here to graphic summary, and I can click here. Oh, it's not going to let me do them all. Let's say we just want to look at the top 5. I don't know if that's going to be useful. Probably should look at some that are not. Okay, this is showing you a coverage. Basically, red is telling you that it's essentially identical, and the first 2 are the same length, and they're pretty much identical. The second one says that it's identical, but there are some pieces missing, and something like that. But if it were a different color, it would say, well, they're close, they're not identical. But the red is telling you that they are essentially identical. Let's go to some different ones, and let me show you how. Here we go. All right, let's go to some at the bottom so we can see what it looks like when they're not quite as similar. Oops, they're checked all. I don't want to check all. Let's go to some of these at the bottom. Get some that are a little different. There we go. All right, so we did that, and then we can go graphic summary. And oh, it's done. And you can see that these don't take up. This is the entire sequence that I put in. It's roughly 8,000 base pair, and you can see that the ones I chose, they stayed the same in this early area, a big gap, and then that are somewhat similar but not very, and then they were highly similar again. This is indicating, of course, this is the region and this is the region. These 2 regions are required for it to be considered a GPX gene. So we would go back and we would say, hey, well, actually, the GPX is down here. This is for the RHOA. So these are the pieces required for the functioning of the RHOA gene, not those just happen to be the ones I clicked on. If we wanted to see which ones were for GPX, we need to find the ones that are GPX. Let's go, not quite so, let's unclick everything. And let's go down to some other organism, but make it GPX here instead of RHOA. Guess we kind of go back. Come on. RHOA. Oh, we don't have many down here. Well, RHOA, the first one. Yeah, GPX is only up there at the top, but I would have liked to have shown you how that would have been. It would have been the same thing except for in later in that sequence, because that's where the GPX is. It's in the second half. They won't give you more. Interesting. I thought I used to do that. I thought. Okay, well, oh, here we go. Can we get more? No, we've got as many as we can. You can also do alignments between them. Of course, it's telling me I need to choose some. So let's do this one, and this one, just to pick 3. And so there are 3 sequences, and it aligned the first 2 together, the second 2, and then the third. So it aligned each one to each other, so that you get several results, and you see where those 3 were similar to one another. So you're getting many because it's like first and second, first and third, then second and third, and then it goes back and puts the other one on top and starts backwards. So that's why you get so many. So 2 of these are essentially identical. Half of these are identical to one another, because they just switched them with a different one on top. But these are the alignments. So you could, if you wanted to look at alignments, you could do it. Now taxonomy, we could click on taxonomy for those 3, and it would show you their relationship. So Homo sapien, we're more closely related here, and this gives you a score. We're not really interested in taxonomy that much, but it was something that it does do. So this is the basics of Blast. Depending on if you don't get anything, like you search and doesn't give you any results, you would click here on the first screen and go more dissimilar or somewhat similar. You would change these here first. That would be the first thing that you would alter. If you put in your file and you blast and you don't get any results, you might choose a different button here, either one of these, and see if you get something. Another thing you can do is we're searching just the standard databases. Perhaps you want to choose a slightly more specific databases, like just RNA sequence or just the ref-seqs. The ref-seqs are the ones who are references that others are compared to. You can also choose the organism. All right, so maybe we just wanted to compare it to Homo sapiens. We would go in. Oops, got the space in. Here we go. If we just wanted to compare it to Homo sapiens, we could just choose Neanderthals. Let's try Neanderthals. They're really close. Let's see what this gives real quick. And see if it changed much between humans and Neanderthals. So we're going to wait the whole time here. As you can see, it might take about 1.5 minutes to search everything. Only takes a few seconds when you narrow the database down. Oh, it said there were no... So, well, that's interesting. either there's a problem here, or there's a major mutation in Neanderthals. I'm actually going to have to look this up now. I know Neanderthals have GPX genes. I've looked it up before, but for some reason this isn't finding it. So I'll have to figure that out. But these are the things you can do with basic Blast. You can search. If you don't get any results, click on these. It'll change your results a little bit, be a little bit more uh, less stringent. So you can reduce the stringency in different ways by clicking on these, and you'll get something. Or you can alter the organism. You can choose just a specific organism you want to, or groups of organisms you want to search in. Maybe you're just interested in mice, so you choose, I just want results from mice. And you can also choose the databases that you search in. As it is, we searched in all databases. All right, and that's about it for basics of Blast.